Okay, we're going to start with Hannah talking a bit about rocks. So why don't you actually come up here so you can see what she's pointing to and doing, please.
Oh, girl, I showered. That place was nasty. Okay. So this is the rock cycle, and these rocks right here are the metamorphic rocks. And the way you get these is from high heat and high pressure, but they don't actually change that much. It's almost like Dr. Webb explained to me yesterday. It's like toothpaste and how you squeeze it, and you can be able to deform the toothpaste when you squeeze it out. So that's what these rocks do, but they don't really change that much. And then these are the igneous rocks, and this happens through weathering, and it's oh my bad. Okay, hold on. The igneous rocks from the volcano, the heat. Sorry, guys. These happen from high heat from the volcano, the ashes and stuff.
It has to melt.
Has to melt. Yes. I'm sorry, guys. And then these are sedimentary rocks down here, and these happen from if you have water flow, really fast water flow, and then the water flow slows down, it'll form sedimentary rocks. So, are we all clear on that? Mm-hmm. Anything else with this?
Well, igneous rocks, you have different types. You have granite, which froze extremely slowly. And because it froze slowly, well, what you had because it froze slowly?
Well, it takes forever to make because it freezes slowly, but there was also that.
Don't worry about that.
Okay.
I'm not confusing.
Okay.
But they grow big crystals because of the slow freezing. And so you can see that black crystal in there? And you can see quartz crystals in there. So you can see the crystals. I love to go to Yosemite, and you can look at these rocks, and you have millimeter or 2 millimeter sized crystals you can see in the granites, which is evidence of very slow slow freezing. These here, the sedimentary rocks, are graded. So the conglomerate has reasonably large size pebbles in it. They're rounded if it's conglomerate because it was rolling down a stream. As you roll, you bounce and you chip off the sharp edges. If it has sharp edges instead of rounded edges, we call it a breccia. So the moon has a breccia surface. It has the sharp edges that have had sedimentation process. You get to smaller size, you have sandstone, which feels like sandpaper because that's what it is. It's sand-sized particles that have been lithified. They've been compressed and cemented together to make a rock. Naturally cemented, not humans doing it. If you get finer material like clays, then you're going to form things like a shale. So the shale feels smooth because you have smaller sized particles. And then this is a completely different thing. This is limestone. It's calcium carbonate. Go ahead.
Do you want to just say do the acid ones first?
Well, talk about the differences, these first ones are the hardness and so on.
So from here up, these rocks are based off of their hardness. And then do you want me to get it out for you? So this one's chalky. It's not supposed to be chalky.
Well, no, it's talc.
So this one is talc, and this is actually one of the ones we talked about yesterday.
It has a hardness of 1. Your fingernail has a hardness of 2.5, so you can scratch it with your fingernail.
So, because I was I didn't want to do it. If you scratch it with your fingernail, you'll have like, it almost looks like chalk. I mean, if you guys want to do it, you guys can. You're like, no. See, that's how I was yesterday. So then, the next section, which is from number 10.
Well, let's talk about which are hard and which are soft. So talc is very soft. What's the hardest one we have in our collection here?
A diamond.
We don't have diamond. Diamond would be harder than our hardest one.
Number 9,
Yes.
which is
It's corundum, more commonly known as sapphire.
Yeah.
Sapphire is when it's single
What?
crystal. Here it's a bunch of small
Why
crystals.
isn't it more blue?
Because sapphire's white. Actually, it's clear. It's perfectly transparent. The blue is because you put impurities in it to get gemstones. Or if you put in chromium, it'll be red, and then we call it ruby. So we have a special name for sapphire that has chromium impurities.
This is the
That color is
hardest
because
one,
of impurities.
and it's a number 9 in the hardness category, and then this is a number 1. So there's the difference between hardness. And then
The next set.
is the streak western cleavage fractures one, and the coolest one in here, I'm going to skip to just the coolest one and then I'll go back, is which one did I say? Was it 21? I think I said it was cool.
It depends on who you are. For me
Yeah.
the coolest one is 11. But
So I thought 21 was cool just because of the texture and the color of it, and then Dr. Webb thought
Well, this is
that one was cool. I can't remember why you said it was cool.
well, this one because I think it's just pretty. It's galena. You feel how it's pretty heavy. It's a dense material because it's primarily lead. So that's
Are you gonna get
a
lead
lead
poisoning
ore.
from
No, you're not.
I asked the
She
same
did.
I asked the same thing. I was like, if that got into you.
So that's lead sulfide.
So
And
these are the
Notice that
streaks. Some of these rocks will streak. So the number 15, which is hematite, is that hematite? If you scratch it on this, well, somebody already did, but if you scratch it on this, it'll be a red streak. And then the other one
well, it has the street colors for all of them there.
So, do you want me to just try some?
Well, sure. Try the pyrite.
Okay, so the pyrite should produce a greenish black streak. I don't know what side to do it on. Or not.
Problem is it's kind of hard. I did this yesterday too. It's kind of hard to actually get it to scratch because it's not that soft. Yeah, I can't really see much on this streak plate, but that's one of the ways that rock jocks, as we call them, will test their rocks. They will test the streak to see what color they leave behind. And the luster, for instance, this, the galena has a metallic luster. Whereas if you look at some of the others, the feldspar, where's my the feldspar, it says a vitreous luster. That means if it was a pure sample, it would be more looking like glassy or watery. And you have the gypsum's supposed to be pearly. Ours is certainly not pearly. Number 19. Yeah, I really that one there is supposed to be resinous or greasy looking. So that's the luster is talking about what it looks like as far as reflection and that kind of stuff. The cleavage, this one here, once again, galena, you can see that it has nice, pretty straight edges. Any place where it's broken on these straight edges. So the galena here has a perfect cubic structure. That means that it would fracture, or not fracture, but it would cleave in cubes if you like sit there. So you have cleave this way, this way, this way, this way, this way. Okay, this one here she brought out. This is obsidian. Anyone like me when you're a child looked for Indian arrowheads every time you went camping? They made them out of obsidian. Obsidian is a glass. What's the difference in obsidian and granite? Any ideas?
denser. Less dense.
They're fundamental. Now, the granite probably is a little less dense, but they're fundamentally the same thing. They don't look at all the same thing. Chemically, same thing. But this here froze really quickly. Because it froze really quickly, it didn't have time to grow crystals. So this we would say is an amorphous solid. And that's what glass is. Glass is quartz that you freeze really quickly. If you freeze it slowly, you get crystal quartz. And so this here, it can hold its sharp edges and stuff because it doesn't have any cleavage. It's amorphous. The structure is non-repeating. Okay. Talk about these here.
Okay. So number 23 is the, it is pretty, is the, if you pronounce it mica? Okay, mica. And this rock, I'm not going to do it because I don't want to ruin it, but this is a rock that
And you're not going to either.
Why don't you look at me?
you can basically peel
You're the
off each, like, you can peel off the rock. Like your blue.
Is this one like that 236?
Yes. And that one actually is separated. It's come apart.
Oh, really?
But these 23, 24, and 36, they're all sheet.
That's cool.
And so you can break them off in sheets.
Are they sedimentary rocks?
That's all you, Christian.
I
know that's
am
how
not
they
sure. You say they are?
I know that's how they formed.
Well, if that's how they form, then they're sedimentary. Sedimentary means that they formed by being laid down and being compacted.
Right.
Let's go to your last trick.
Oh, this. Okay. So we're gonna put some acid on some of these rocks, which I just.
This is the acid test. You've heard the term. This is the acid test, and this is in terms of
So we're gonna take.
geology, and try to get on your hand because that is acid.
We're gonna take number 3. We can get it out. You want on that?
Yes, yeah.
Okay.
Go ahead and set down. Don't hold your hand.
Okay.
Now she's going to put some acid on there. Right there. See it bubbling?
Cool.
That bubbling is a result of the acid attacking the carbonate. And so it's separating. You have calcium ions, oxide coming off the bubble. And so we put the acid on so we can see if it has a carbonate. So let's take another example, one that looks, well, let's see, I don't know what is tin. Okay, this is microcline feldspar. It looks reasonably similar. Nothing, because it doesn't have carbonate. So this, every good geologist has his little acid so that he can test a rock, because sometimes it's hard to tell what rock is what. Now, here's another one. This here. Put it on the dirty part. We'll clean off the dirt.
Oh, cool.
Okay, pretty strong reaction, right? What does that mean?
Carbonated.
It's carbonate. In fact, these are the same thing. Rocks look different even if they're chemically the same because
This
you
one?
have.
Just dried faster. This one than that one.
No, we had that one. We did.
Freeze faster.
Oh, okay. Now I understand what you're saying. This one here would have been probably the slower one,
Really?
so that it formed a nice single crystal. This is a single crystal of calcite, whereas this here is, I believe, a whole bunch of them. Either that or it's got some impurities, right? The reason it doesn't look glassy.
So
It still has,
It's kind of like ice when there's air bubbles.
right. It still has the basic crystalline structure of this. So it's probably more inclusions or, fractures and stuff.
So if there's like bigger crystals, that means it formed fast.
Slow.
Slow.
Because the crystals take time to grow. Now, just some other things. Well, we got some magnets here. Some rocks contain iron. Actually, let's see if these three here have reasonable amounts of iron. So let's see if any of those will pick up a. That won't. We didn't test this beforehand. Yeah, that won't either. Well, one of these, it says, is a lodestone. The lodestone should actually be magnetized to pick stuff up. Here's a magnet.
Oh, cool.
Clearly, that has some iron in it, right? As does that.
Cool, actually.
This one has iron. It's red colors because of the iron, but it's not strongly magnetic. It's hematite. The iron, the heme, same thing that makes our hemoglobin red. See if there's any others that are. Okay, so that one's got some metallic, some magnetic stuff in it. So if we look at the talc, it's magnesium silicate, Mg3, Si4O10. That's crazy. And then OH2, that's in water. So what's the magnetic material here? It must be the magnesium. Think about that. Nope. So that's another test you can do to see if things are magnetic. We already tested those. Lead's not magnetic, or not strongly if it is. Nope. Okay. It gets boring after a while.
Ooh.
So what is 48? We look down here at 48, and 48 is basalt. Basalt, this is the kind of stuff that you have on the seafloors. It's magnetic. Because of that, we have on the seafloor the magnetic history of the ocean. And sailors noticed that their compasses were acting wonky as they sailed over oceans. And so scientists studied, and they found that you have actually magnetic fields frozen into the seafloors because they have some iron in the rock. Okay, just going to point out one last rock here. This one here, it's a very important rock. Looks a lot like this one, right? But you can see a difference. This one has kind of a yellowish brown tint that this one doesn't have. They're completely different chemically. They actually feel a lot like her. They're both light.
Oh, yeah,
Like, there's a lot alike. But they're nothing alike in reality. One of them is coal. It's called hard coal. It's actually a coal that has the highest energy density. It's over 90% carbon. And the other one is obsidian, which is a glass that is a silicate-based material. All right. Thank you.
Is this one the coal?
Yeah, that's the coal. Now, rocks is my weakest area in geology, right? I have to admit my weakness is I am often, floundering about trying to figure out, now what kind of rock is this? What kind is that? We have a piece of granite that we picked up in Colorado. So I believe it's granite. What if I'm wrong? We looked at this here when I was going over these with Hannah beforehand. I looked at this and it says granite gneiss, Gneiss is nice. I looked at that and this granite, I'm like, I can't tell the difference. But the granite gneiss is supposed to be metamorphized. It's been heated under pressure and deformed a little. And so there are differences. This one down here, marble. If we'd done the acid test on the marble, it would have bubbled. Because marble is metamorphized calcite. Marble is metamorphized this or this. These dissolved in acid. They also, at a much, much slower rate, dissolve in water. So if you put marble in water, over time it will dissolve. And if you have acid rain, over a much shorter time it will dissolve. For the same reason that we saw them bubbling here in the hydrochloric acid. Yes?
Islands that are made out of marble, why don't they like react if like something's spilt on them?
I think they put a sealer on them because otherwise something that's acidic, like let's say if you have pineapple on it, will be etching it. And so if they don't put a sealer on it, you're going to have it degrade more quickly. Now we've already, oh yes, wait, this wasn't supposed to be here. I deleted these slides. Oh, criminy. Well, I made a new presentation, but apparently this is the old one. Okay, how we classify minerals. Now, what was the difference in a mineral and a rock?
Can a rock have more than one compound in it?
Yeah, rocks are made of minerals. Minerals are the naturally forming chemical compounds that are crystallized that make up the rocks. And so the minerals are the fundamental pieces that go into making a rock. And so we classify them by their form, that is what their shape looks like. You can see this one here, and its form is something that's very distinctive. We classify them by their hardness. So, we did the example with the talc, you can scratch it with your fingernail. Well, some other things that people will use is like a piece of iron. If you can scratch it with a nail, then it's, I think a nail is around 5, so you can separate harder and softer. And so they try to identify the hardness of a mineral to determine what it is. And I'll have another slide where we talk about the hardness. I think I went really quickly through it on Friday. Cleavage and fracture. Cleavage, you take a straight edge, you line it up just so, and you hit it with a mallet, and it goes and splits. That's what cleavage is. Not all minerals will cleave. Ones that don't cleave fracture. That is, it just shatters. Whereas cleave, it cuts in a certain manner. And so if you have nice visible faces on your minerals, then they have a cleavage plane. The color, it's very obvious. And the density, you saw the difference in galena being very dense, whereas the coal and obsidian were fairly low density. So you could have felt the difference in those. So let's go past that. Crystallization, for something to crystallize, you have to have the right conditions. You have to have the right temperature, pressure, and space for growth. So if you just mix chemicals, it's not necessarily going to crystallize. The concentration is a real big issue. So let's say you want to make a sapphire. You have to have a fluid, like I think water is the medium they use, with the right amount of aluminum and oxygen dissolved in it for it to crystallize and form the crystals. And so they keep the temperature just so, they keep the concentrations of the aluminum and oxygen just so. And then they can slowly grow their sapphire crystals. And the process is pretty complicated, which makes sapphire reasonably expensive. How do I know? Because that's what I did research on. So well-formed minerals aren't so common in nature because you have to have just the right conditions. So a diamond is another crystal. Diamonds that you find tend to be really small because you don't have the right conditions for long enough time to grow a large diamond.
We were talking earlier in the year about how you can make diamonds.
Yes.
What's to stop everyone from doing that and making a lot of money?
The diamond cartel, primarily. They do things like they convince people that it's not as good to have a perfect diamond. That it's better to have one that nature made with its imperfections. And people believe that. Now, it's not cheap to make the man-made diamonds either, but they're cheaper than the gemstone diamonds because the gemstone diamonds are controlled by one company essentially worldwide, and they thus control the supply and the price. So I am personally not a fan at all of the diamond cartel, and if I were to buy a diamond ring, I would buy a perfect diamond rather than one of the cheap natural ones that are more expensive to buy.
Is Amy's the perfect diamond?
Amy's is the one that her grandmother had. So it's a natural one. It's only in the last couple decades they've been able to make synthetic diamonds.
They're completely chemically the same,
Yes,
except the impurities.
right. And that you can introduce whatever impurities you want for a man-made diamond. So you can replicate just about any type of diamond. Okay, the crystal in nature. Here is a picture of what a diamond looks like and its structure. The structure for the diamond is actually very complicated. It's, if I remember right, it's something like a face-centered cubic with 3 bases, or maybe it's it's a complicated structure. Graphite is made out of exactly the same material, but graphite forms these hexagonal rings, and those rings form sheets. So graphite is like the micas we saw here. It forms in layers. You might know that graphite is used as a lubricant. Because you have very, very weak forces between these different layers of the sheets. And so they break it up into little pieces, and you have very weak forces between the layers, and it slides very nicely. Here's a picture of a real diamond. Now, this diamond, if you look at it, you see that you have a flat surface right here. And then you have another flat surface that's over here. You have a flat surface here.
They
Go ahead.
always cut diamonds like that. Why?
This is, I think, there's a name for the cut. I don't know if it's brilliant cut or if it's something else. But what they do is somebody has to sit there with his little razor blade and his mallet and very carefully line up and break them on those planes. So those are the natural cleavage planes. And the reason they do, which was your question, is because light goes really slowly through diamond. Because it goes really slowly, if you have light that comes and hits the diamond surface at an angle like this, it will reflect out. And so the design here is so that light comes in and bounces around, and it will only come out at very specific angles. So you have light coming in the whole front surface and then only coming out in certain small areas. The result is it's very concentrated. So you look into that diamond, you see it twinkle, if you will. You see a bright flash and a bright flash when you're looking at the right angles. And so that's what they're looking for in the diamond. That's what people love about them, is that brilliance. And so that's part of why they cut it this way. What's this right here? That's a lump of coal. And if you were Superman, you crush it and you form a diamond, right? Yes.
Are those videos on like Facebook true where they like put peanut butter around a lump of coal and then put it in ice and then they pull back the coal and then there's a diamond inside?
No. Funny, but no.
It looks very inventive.
I've not seen that one, but it sounds good.
You should watch it.
Yeah, we should watch it, sure, because that's educational. And here's another prank you can do. Now we'll watch people pretending to pop popcorn with their cell phones. And then charging the cell phones up in the microwave, because, you're going to cover the things you can't do. Diamonds are the same fundamental thing as coal. And so that's why somebody would do something like that as a joke. But it takes enormous pressure to be able to convert a diamond into coal. And you're not going to create that by putting in peanut butter and then freezing or whatever. Okay, hardness. Hardness is measured with the Mohs hardness scale. Hardness, like I said, you can do comparatives. So remember I said the nail was about 5. It's actually about 6.5. So here we have common things that you can have to test the hardness. So you have something and you're not sure if it's quartz or calcite. What would your first test be to differentiate between quartz, silicon dioxide, SiO2, and calcite, calcium carbonate? Acid. The acid test would be your first one because the two fundamentally look alike. But if you put them in acid, only the calcite is going to react. But if you don't have acid, you might say, well, let me take a glass plate and try to scratch it. If the glass plate will scratch it, it must be calcite because calcite is softer than glass. If it won't, then it must be the quartz because it's harder than the glass. And so that's a way of differentiating. So you have a number of things with you. Everybody has fingernails, at least one. And so you can always test, see if it's one of the really soft things or not with your fingernail. A penny would tell you, in theory, a penny would differentiate calcite and quartz as well.
If it's a copper penny.
I believe this is based on the current penny, which is, what is the current? It's actually covered with copper still, so it would behave like copper. Yeah, it's zinc on the inside. Actually, I think it's covered in copper. Who knows? Here's how the hardness is actually measured. There's scientific measuring method. You have a little diamond indenter, and you push it down with a certain amount of force, and you measure how big the hole is it makes. If it makes a big hole, it was soft. If it makes a small hole, it was hard. That's actually how you test for the hardness of a material. That's the definitive test. But, you're not doing that out in the field. You're just scratching and comparing. Here's my slide on cleavage and fracture. You can see, so muscovite was one of our micas. And the muscovite, you see, forms layers like we saw when we looked at it. The muscovite was this one right here. 24. No, this is the biotype. So this is the muscovite. This is the one that's shown there. And it forms in layers that are easy to see. Now the feldspar, and there were a couple examples of feldspar here. It looks more like, not logs, like 2x4s stacked. And then we get to things like halite. What's the more common name for halite? Halite is the name for NaCl. Yes, more commonly called salt, table salt. And so halite forms cleavage on 3 planes. And then we have this last one that's shown here, calcite. Notice its planes are not 90 degrees. The halite was 90 degrees, but the calcite is not 90 degrees. And so when we looked at the calcite crystal, you saw that these are not squared off edges. And so that's another way of differentiating one material from another. Hey, there was still some acid on that. Nice job, Richard. Just a little acid. Colors. I have this here specifically because, as you know, I did research on these. This here, those are all different forms of the same thing. They're all Al2O3, what we call aluminum oxide. What's the difference in the ruby, the one that you recognize as a sapphire, and the one that I recognize is a sapphire. I recognize the clear one because that's what I work with. What's the difference? Impurities. So different impurities can give you different colors. So this is chromium impurities. The sapphire, I don't remember if it's iron or cobalt. I'm not going to write down because I don't remember. But you can have different impurities, and you can have sapphires that are different colors than blue or red. You can have a green sapphire or a yellow sapphire. That's just putting different impurities in to get the different colors. And so here's some more pictures of naturally occurring sapphires. And you see these are reddish. They're going to be called ruby. These are yellowish, and this is clear. And what was that?
Go back. One slide, please.
This one here is another slide that I took out when I was redoing it. When we classify our minerals, now on this sheet here, I put the chemical formulas for the minerals that we have. And we have things like microcline feldspar, potassium, aluminum, silicon 3, oxygen 8. They're sometimes pretty complicated formulas. Biotite, we were looking at, muscovite, the one we looked at just a minute ago. It's KF2, Al2O3, 3, that's 3 of the sapphire units, 2 of the KF units, and then SiO2, 6 of the silicate units. So it's pretty complicated formulas that go into these. But 90% of our rocks have that SiO2 in some variation, right? I read the microcline Si3O8. Well, that's not a, SiO2 would be a 1-to-2 ratio. That's not a 1-to-2 ratio. But it's a silicate, it's still silicon oxygen compound. So 90% of them are silicon and oxygen compounds, along with these are common metals. Just to make sure we know them. What is Al? Aluminum. If we were in Great Britain, what would Al be? Aluminium. Mg? Magnesium. Mn? Manganese. Fe? Iron. Ti? Titanium. Tin is Sn. Okay, so those are some of the common metals that you have also in your rocks. Here's the basic unit of a silicate. Notice I said it's SiO2, but this here is SiO4. And any reasonable person says SiO2 and SiO4 are not the same thing. What happens is you'll have this little tetrahedron, and then this tetrahedron has the silicon in the middle and then the oxygens around. Well, if you bring another oxygen, that oxygen could go with another 3 of those and just have one more silicon necessary. And so each face can have oxygen and then just one more silicon. And so if you have a whole bunch of these all packed together, that's how it goes from SiO4 to SiO2, because you're stringing them together in repeating units. I don't know how far I want to go into minerals, especially since we only have 10 minutes. Some minerals have lots of iron in them, and those we tend to call felsic. Some of them have small amounts of iron in them, and those we tend to call mafic. I said that. Well, either I wrote it wrong or I said it completely wrong. Felsic is actually feldspar. I said that wrong. I also apparently am channeling my inner dyslexic there. Granite is felsic. Granite is more than 35% feldspar. Mafic has large amounts of magnesium and iron. So magnesium iron starts with F. That's where you get the mafic from. And the felsic comes from feldspar. Feldspar is just German for field rock. It's the kind of rock that was found a lot in Germany. And it's actually half of the Earth's crust is that feldspar. So it's a very, very common rock. Non-silicates, things that don't contain silicon dioxide, are only 8% of the crust, and they include things like what we see here, galena. Remember, galena was about my favorite rock. Pyrite, the fool's gold, calcite, hematite. Our sample of hematite is very red. You don't have to use a street plate to see it. Gypsum, spinel. Those are some non-silicate minerals that are common. So here's a classification table. All minerals can be broken into, are they silicates or non-silicates? Just as a reminder, what percentage are silicates?
More than 90.
Okay, more than 90. I'm going to put 90%. I'm just going to round to 10. Our previous slide said that 8% were non-silicate. So I'll put the 8% there for non-silicates. So most minerals are silicates. Doesn't mean you can just assume it's a silicate, but that's the majority. The silicates can be broken into ferromagnesian and non-ferromagnesian. Well, we did that test with a magnet. Ferromagnesian means it'll react to a magnet. And so the ferromagnesian tend to be the non-ferromagnesian felsic. You see potassium feldspar, sodium calcium feldspar, common ones there. If it's a non-silicate, you separate them between carbonates. How would you test if it's a carbonate or not? Acid test. So things that are acid here, sulfur here, and then you also have halides versus phosphates or native elements. Native elements are pure. Pure gold. I would like to have that. I've tried to take out all of those quizzes, but obviously there's failure. Okay, now to the cycle of rocks. Okay, we had Hannah, she the cycle of rocks and introduced looking at the rocks. We have minerals that can form either from molten rock or in water solutions. Molten rock, fire, igneous rocks. So igneous rocks are rocks that formed from molten material. You melt it, it freezes. Water solutions, those are going to be sedimentary type rocks. Now, when you're forming crystals, and I know I had a question on this on the test last year, the first minerals to crystallize from a magma are going to be those with the highest melting temperature. That makes perfect sense. You have a hot, melted material. As it cools, the things with the highest melting temperature are the ones that are going to solidify first because you reach that temperature first. Things with the lowest melting temperature are going to solidify last. So you start to have the things that have high melting temperatures freezing, and the material that's left over is missing the things with high melting temperatures. And so silicon, the silicate concentration is going to change as you go through. So the first ones to freeze have the lowest amount of silica. The silica is a low melting temperature. So when things start to freeze, first things that have small amounts of silica are going to freeze, which means the amount of silica that's left is going to increase. So you're going to start by making more mafic things, and then as the freezing continues, you'll start making the more felsic things. So this graphic over here has information to help us get it straight. So things that have a low silicon content have high melting temperatures and are the first to freeze or the last to melt. And conversely, things that have a high silicon content have a low melting temperature, and thus, I like how that's not the right word, are the last things to freeze or the first things to melt. It should have been first down there where it has M. I don't know what I did wrong. I clearly made a mistake in that graphic. We are almost out of time. Hannah told us about the igneous rocks, the sedimentary rocks, and metamorphic. Metamorphic rocks are still fundamentally either igneous or sedimentary, but they've been metamorphized. They've been changed by that high pressure and temperature, and sometimes water is involved as well. So they look different. So, marble looks different from calcite. What is the feature that stands out in marble?
It has multiple colors.
Okay, multiple colors. And, the swirls is the things that stands out. And those swirls come because of the deformation that occurred. You started with a calcite that assumedly didn't, had straight lines and stuff. And then as it metamorphized, things got deformed, and that's what creates the swirls in it. Also, if you look at this, you'll see that many of the metamorphic rocks just kind of have a shininess to them. That's also a result of them being heated a lot, not completely melted, but heated to where it softens and gets those shiny structures. I've already talked about the difference between magma and lava. Magma is inside the earth. Lava is outside. Okay, let's have a great start of the week.
Can you go back to the slide where it's right after the ferromagnesium slides, but it's like the non-slides? Yeah, the one before it.
No.